So, good afternoon, everyone. Welcome to the third lecture of the Fabio Anzà about the geometric picture of quantum mechanics. Thank you, Fabio. It's your show.
All right. Thank you, Leah. Let me pull up the lectures. Can you see my screen?
Yes.
All right. Thank you. All right. Welcome back, everyone. So this is the third lecture of the mini-school on geometric quantum mechanics. And so for today, what I have in mind is to finish some material that I was trying to cover in lecture 2, and then go through some of the kind of more recent applications of these ideas. I've been using these ideas for my own research, and I'm going to present some fun and interesting directions. All right, let's go with a quick recap of lecture 2. So we, in lecture 1 and 2, actually, together, we looked at the quantum state space. We realized that the Hilbert space is a redundant description of the state space of quantum systems. And by getting rid of this redundancy, one completely identifies the quantum state space, which is a complex projective space of dimension d-1, where d is the dimension of the Hilbert space. And we learned that this has particular geometry that is mostly given by the fact that it's a so-called Kähler space, which means that it has two notions of geometry. One is symplectic geometry, which is basically the geometry of classical phase space. And the other one is Riemannian geometry, which is the appropriate notion to compute length, areas, volumes, and stuff like that. The interesting thing is that these two notions are fundamentally intertwined. And actually, the reason why they work with each other so well is the existence of a third structure, which is called a complex structure. But this goes beyond our current scope. Now, we've looked at some of these aspects. The symplectic aspects, I'm just going to mention a couple of them. First one is that you actually do have canonically conjugate coordinates, and an example are the usual probability phase coordinates we put on quantum states. And the other one is that if one look at unitary evolution, basically Schrödinger's equation are Hamilton's equation of motion in disguise. So if one basically builds a geometric picture of quantum mechanics, you see that Schrödinger's equation turns into classical equations of motion. And then we looked at some of the Riemannian aspects. I've mentioned the notion of Fubini-Studi distance, which is the fundamental notion of distance in the quantum state space. And we looked at its statistical interpretation as basically statistical distinguishability. And of course, the main reason why technically this is important is because it gives us a volume form. So it allows us to define in an appropriate way the notions of integrals on this state space. And so let me remind you what this means. So the setup is the usual one. We have a system in a Hilbert space H. The dimension of H is D. And then we embed this. We make a choice of a basis. Alpha goes from 0 to d-1. And then we have this C alpha, E alpha, and E alpha is a basis. Beta. And the dimension is d-1. So Z belongs to CP d-1. The appropriate notion of volume is a so-called Fubini-Studi volume, and it's defined as square root of the determinant of the metric dz dot dz bar, where this is the back measure. And for example, for a qubit, so when we have something like this, with probability phase coordinates, you get the following: dp, d phi, and normalization can be chosen actually at will, depending on if we want to scale the total volume. So as I mentioned at the end of the past lecture, this means that if I have a scalar function, see, such that from CPN associates a real number, then it makes sense to write the following dp Fubini study, because this is independent on the coordinate system that we use to compute it. So this would mean, for example, f of p phi, dp d phi divided by 2 pi, and the two integrals are p goes from 0 to 1 and phi goes from 0 to 2 pi. All right. So before we go to the main topic of this lecture, which is basically how do we deal with uncertainties, mixed state probability distribution in this space, and it is we'll look at two interesting things. One is the standard uncertainty principles, but since we really don't get too much insight by analyzing that, we'll look at the time energy uncertainty principle. So what is the standard uncertainty principle? Is obviously in quantum mechanics, we have observables that don't commute. And this is, in standard quantum mechanics, this is what it means. And in geometric quantum mechanics, this just means that when I take an observable and I map it into its geometric function, which is, let me call it like this, f of c z a z divided by z. So it's basically the expectation value and renormalized with the norm of the vector. Then the commutator is mapped into f, and let me call this fa, fb is mapped into the Poisson bracket. Now, this is the crucial object to look at the uncertainty principle. This can be written as f a omega a b f b b, where this is the symplectic to form, and these are the vector fields associated with FA and FB. And one thing you need to know in order to understand Heisenberg's standard formulation is that if we have a function like this, then if this is my manifold, then I can foliate the manifold in hypersurfaces at constant value. So these are surfaces where fa of z is equal to some a that belongs to a min and a max. And once I have this level set, I can look at the gradient. And this gives me a vector field, which is defined by CFA is GAB delta B of FA. There you go. And this is just the gradient. It's just written in a coordinate agnostic way. So if you define this vector field, you can check that the following is true. FA, GAB, FB is, and this is associated with the observable A. This is delta A, which is the variance. of the, actually delta is squared, yes, it's delta A squared, which is the variance of the operator. So in standard way, we would call it expectation value of A minus expectation value of A squared. All right. So why is this relevant? Well, because in differential geometry, when you have these kinds of vector field, you have the following inequality, which actually it mimics very much the way the Heisenberg uncertainty relation is proven, and it's the following: G A B F A F B G A B G A G B is larger or equal than GP. I think there is a square plus FA omega A B G B square. And you see this, as I've shown here, this is connected to the fact that this is non-zero is connected to the fact that the corresponding Hermitian operators don't commute. And so basically the standard uncertainty principle comes from ignoring this term. But as we know, this can actually be strengthened by leaving this term. It's going to give us a tighter inequality. But the standard approach is obviously the same. Now, a bit more, I think a bit more interesting is the so-called time energy uncertainty principle. And the derivation and interpretation that I'll be giving is one of the possible one, but I think it's kind of the geometric aspect of it makes it a bit more general, at least in its concept. So if this is our quantum state space, and let's imagine that we start with a state psi1 and we end in another state psi2. We make a path and we ask, what is the minimal amount of time that I need to get from psi1 to psi2? Now, this is literally the way we define the Fubini-Studi distance. So we do the integral from 1 to 2, ds Fubini-Studi, and we will, this is the length basically, L1, 2. Now, if this evolution is generated by a Hamiltonian, it means that at each time step, the vector that generates the transformation is constant because it's given by our Hamiltonian. And indeed, you can check that the following are true. Integral from 1 to 2, since ds Fubini-Studi square is, as usual, GAB A dxB. And the path is defined so that its derivative is basically FHA, right? Is the function that is associated to the Hamiltonian Hermitian operator. So that means that when we look at ds, we're going to have square root of GAB, gamma dot A, gamma dot B, dt. And so this is just going to be delta H, delta T, where delta T is the time that it takes me to go from 1 to 2. Now, you can check that what this means, that you can use the following concrete result in this way. First, you realize that basically what this means is that if I look at this picture, the speed of my point across the quantum state space basically depends linearly on the variance. So this means that the system goes through regions with higher uncertainty faster. Now, the other thing that we learn is that if we are asking, what is basically, if I want to build, if I have a reference state and I want to build a state that is fully distinguishable from this state, I can ask what is the minimal amount of time that I need to evolve my state for that to happen. And the orthogonalizing time, this is the orthogonalizing time, and it's the request that the length between the initial and final state is the maximal possible, is pi/2 in the Fubini study distance, because let me remind you that we have the following relation: cosine of the Fubini study distance between psi and phi is the modulus of psi pi. So when this is 0, this has to be pi/2. So the length has to be pi/2, which means that if I need, for example, if I need to build a hardware that performs a certain manipulation on my system, and I need to be sure that the manipulation that I do on my state produces an orthogonal state, then I need to wait a certain time t that is at least the time where L12 is going to be pi/2, right? So this means that t is larger than tau, let me call this tau orthogonalizing time, and you can check that this is pi/2 delta h. Now this, actually, let me call this delta t, this delta h delta t larger than pi/2, and I'm obviously ignoring h bar factors, but you can put it back. Now, this is basically one of the derivations of the so-called time energy uncertainty principle, right? And it is the fact that the notion of scalar product being equal to 0 is it's something that has operational meaning, and it's about distinguishability, right? It's about the fact that two states are orthogonal to each other when there is an observable that allows me to completely discriminate between them. Now, these states are obviously useful, especially, for example, if we're trying to build a computer with them, because they're being distinguishable states. They're the states we can use to store and to perform calculations with. And so understanding the fundamental limit with which a quantum computer operates is actually a field of active investigations, because there is a lot of interplay between the fundamental limits, like this one, and the practical limit in which we have a finite amount of resources that we need to use. And we would like to have a way to implement this notion of having a limited amount of resources within the formulas. This can actually be done in a variety of ways, and there are a lot of people working on these kinds of approach. But I really wanted you to have a rough idea of what does it mean, what is the time energy uncertainty principle within this geometric formula, because I think it's a very elegant and simple derivation that kind of clarifies the meaning behind the time energy uncertainty principle, and why conceptually and practically this is actually different than the standard Heisenberg uncertainty principle. All right. Next step. And this is actually the bulk of the lectures today, and it's dealing with uncertainties, right? Random quantum variable. So from now on, we will not be discussing the properties of the quantum state space, but in the formalism, but we will be using it. So we'll be using it to build a basically a theory of a statistical mechanics on the quantum state space. So the fundamental notion, so we have our manifold, which is CPN, and statistical mechanics was born in order to cope with uncertainties, right? In that case, for example, if we look at the kinetic theory of gases, there's just too many particles, right? And we're not able to track every one of them. So what we do is that we use statistical techniques. And the idea here is very similar, right? If I have the picture that geometric quantum mechanics is leading us to is the following. I have a quantum state space, which is the state space of my quantum system, and this is continuous, it's not discrete. A point in this space is a pure state, right? Z corresponds to, we call a projector, right? Psi psi. So this is a pure state, and as in classical mechanics, pure states are those states that have phase space entropy 0, right? And one of the notions here is the notion of entropy, which is basically, well, pk log of pk is the standard Shannon entropy, which is identified with H, right? These are configurations in which we know exactly what the state of the system is. But what happens when this is not true, right? When we don't have perfect knowledge and we have a certain probability distribution on this? Well, things progress basically as usual, because we now have a good notion of how to do integrals, and that means that we know how to do measure theory on this space. So what does that mean? Well, in practice, this means that you define the concept of random quantum variable. And this means that basically we're thinking of Z as a random variable that can have that, you know, as its possible sampling space is the full quantum state space, and Q, and it follows a certain probability distribution, and this probability distribution I usually indicate with Q, and it's the notion of geometric quantum state. And I usually say that Z has a certain probability distribution Q using the standard notation of probability theory. Now, bear in mind that in this setup, sometimes we use a particular notation which goes as the following. What this means is that the probability of finding that the state of my system will be in a small volume around, this is, let me call this Z now, around Z is defined like this, is dp around Z is Q of Z dv Fubini studi in the Z coordinate system, right? So this means that we have a probability distribution which can be smooth, or it can be, for example, a linear superposition of pure states, and QZ is the probability density. So it's I call it the geometric quantum state. And for people who are wondering, what about the density matrix? Now, this is actually a more fundamental notion of the density matrix in the following sense, is a precise sense, in the sense that rho is just the integral over dv Fubini studi Q of Z of the projectors Z. So this means that if I have the geometric quantum state, I can compute the density matrix, but not the other way around. A density matrix can be the result of different geometric quantum states. But the crucial thing is thanks to the geometric formulas, we have a full way of manipulating and operating on QZ. Now, let me go through just three very simple examples of geometric quantum states that are meaningful and useful. First one, pure state. So a pure state is just a point, right? It's some z0. How do we associate a probability distribution to this? Well, it's simply the so-called Dirac measure. See, right? And we physicists usually write it like this, right? Which means that this is the Dirac delta function, which is 0 everywhere, but when z, it's exactly the required point, z0. In that case, that's infinite. But the reason why this is the more practical reason is that if I have an observable A of z, let me remind you, this is defined like this. Then, what is the expectation value of A with Q? Well, this is defined as the integral with dv for b is 2d. See, Q of z. I'm just going to write A of z. Now, this means that if Q of z is a Dirac delta, then E delta z0 of any A, this is just going to be A of z0, which is z0, A, 0 divided by z0. Z0 as it should be. All right, so pure state corresponds to a situation where the probability that the system will be in any state but z0, it's going to be 0, and therefore the probability that the state will be z0 is going to be 1, and that should be reflected in all our expectation values. Now, this as an obvious, simple linear extension, and as a convex combination of pure states. Convex sum of pure states set J. So these corresponds to Q of C is just a sum over J that goes from 1 to some finite number N on the J delta of Z minus ZJ. And I should be a bit more precise about this. The way I'm writing this delta of Z minus Z0 in a coordinate agnostic way, but the precise form depends on the specific coordinate system. And for us, in order to have an invariant quantity, you have to be a bit more careful with the geometric aspect, and you have to play the same trick that we played with the Fubini-Studi measure, where we multiply the Lebesgue measure by the determinant of G, because that allows us to basically extract a coordinate invariant part. And so it's the same situation. So this means that, for example, if I go from p phi coordinates to theta phi coordinates in the qubit state space in CP1, I'm not on delta of p phi minus p0 phi 0 will not go into delta of theta phi minus theta 0 phi 0. There are certain transformation rules that are basically the same that we had for integrals that allows us to extract a coordinate invariant notion of delta. But as for many of these things, the advantage of using probability coordinates is that delta of z minus z0 in probability coordinates is simply 1/2 delta p minus p0 delta phi minus phi 0, where z0 is just equal to 1 minus p0 square root of p0 e to the I phi 0. All right, so let's get back to this. So this is in the case of a convex sum of psi j. What do we have? A q. This is sum over j, lambda j, and then we have the integral dv for b studi a of z, delta of z minus zj, and this is trivially sum over j lambda j, a of z j, as it should be, because again, if we compute rho, this is just integral dv for b studi q of z cz, and this is just going to be sum over j lambda j zj zj, as it should be. So the general rule, if one wants to be explicit in the coordinate system, in the homogeneous coordinate system, we have the rho alpha beta is the expectation value for the state q, so rho alpha beta q, the one that comes from the geometric quantum state q, z alpha, z bar, beta. And so, for example, let me give you a concrete example for the case of the qubit. Case of a single qubit, this is just 1 minus p, square root of p1 minus p e to the I phi, square root of p1 minus p e to the minus I phi p. This means that rho 0, 0 is 1 minus the expectation value over q or the coordinate function p, and obviously rho 1, 1 is just 1 minus rho 0, 0 because rho is normalized, and then we have rho 0, 1 is just the expectation value over q of square root of p1 minus p e to the I phi, and rho 1, 0 is obviously rho 0, 1 start. All right, so these are two examples, right? Pure states are a Dirac measure that correspond to the situation where all the probability mass it's in one point, or you have linear extension of that convex combination. But one can obviously wonder about the existence of continuous measure. They're obviously there, and one of the most natural one to consider comes again from it comes from thermal equilibrium, and it's obviously e to the minus beta, some epsilon of z divided by some partition function q of beta, where q of beta is just the integral dv for b to z e to the minus beta epsilon z. Well, in this case, epsilon of z can be anything as long as it's an observable function. But in particular, for statistical mechanical application, this is going to be the expectation value of the z of the local of our local Hamiltonian, right? And this is a continuous function of z, and so this means that this is a continuous measure over the quantum state space. And notice that this is actually very different from the standard partition function that we typically use, for example, in quantum statistical mechanics or in the statistical mechanics of finite-dimensional quantum system, where this is usually, the ensemble is usually taken to be the following: e to the minus beta E0 divided by z beta, delta of z minus z of E0, so e to the minus beta E1, z beta delta of z minus z of E1. Now, the difference between these two cases, I think it's quite evident. If this is, you know, my my manifold, the quantum state space. In this case, what I have, for example, in the case of qubit, what I have is just 2 points, say here and here, this with probability e to the minus beta e0, and this is to the minus beta e1. Now, in the other case, what I have is like a smooth interpolation between these two situations in which the geometric quantum state changes in a continuous fashion. But obviously, in some sense, this is still thermodynamic equilibrium, and you can actually prove that you can build a whole quantum thermodynamics out of it, and it looks like it's slightly different than the standard thermodynamic that you get when you assume that the state has this form, or that the probability or the density matrix has the so-called Gibbs form. All right. So you have pure states, you have convex combination of finite convex combination of pure states, and you have continuous ensembles. So these are three constructive examples of geometric quantum states that are interesting to study. Now, let me go back 1 second to the overview. All right, so how do we use this in practical physical situation? So there are, I've prepared consideration on at least 3 physically interesting cases. The case in which we have an open quantum system where, and this is obviously the case where our system of interest is in some ways smaller than the rest. Let's imagine, for example, an atom in a certain cavity where this cavity is filled with electromagnetic field, and obviously the state of the system is described by, for example, if it's a 2-level atom, is described by CP1. But obviously the state of the field, the atom interacts with the field and exchanges correlation with the field. And why one would like to build a general theory for how this occurs. So this is the theory of open quantum systems, and it has to do with understanding how systems that exchange energy and correlations with their environments, how they interact with each other, how they behave. Now, obviously, associated with it, there is the notion of entanglement. Now, for people who haven't met entanglement yet, entanglement is one of the fundamental aspects of quantum mechanics, one of those that really sets it apart with respect to classical mechanics. And there are interesting geometric aspects to entanglement that we might be able to cover either today or tomorrow. But the notion of entanglement, as I'll show, is an interesting one to study, and you can use geometric quantum states to study, for example, how the ensemble that gives you entanglement behaves over time. And the third situation is actually state preparation. So it's very kind of experimentally oriented, and it's about trying to describe, as I said at some point at the beginning, is using geometric quantum states to describe state preparation is about trying to factor in the resources that we need to build a certain quantum state, either for computational purposes or for experimental purposes. All right. So first, open quantum system. So this is kind of the crucial derivation, and it goes like this. We have a joint Hilbert space, which is the Hilbert space of our system, HS, and the Hilbert space of an environment, HE. And we assume that the overall, the joint system is in some pure state, CSE, that belongs to HSE. Now you can prove that, well, first let me define AI. I goes from 1 to the dimension of the system. E alpha, and alpha goes from 1 to the dimension of the environment. And these are bases, respectively, orthonormalized bases, respectively in HS and HE. Now, generic state psi can be written as sum over I psi I alpha, AI, E alpha. And you can play a little trick and you can prove that you can always write this in the following way. Square root of Y alpha, so Y alpha, E alpha, where Y alpha is just the sum over I from 1 to the S, psi I alpha modulo square. So, yeah. So this is basically the probability that if I make a measurement on the environment, and this measurement, it's a projective measurement on the eigenbasis E alpha, then I get the alpha result with probability Y alpha. As a result of that hypothetical measurement, the state of my system is going to be Y alpha, and this is just sum over I psi I alpha divided by square root of Y alpha AI. So a couple of comments on this very simple derivation, and should go down. So for people who are familiar with the so-called Schmidt decomposition, this is actually very similar to the Schmidt decomposition, but it's reversed. In the Schmidt decomposition, we have something along these lines. Square root of lambda I, and some psi I of the environment, right? So the sum, the label, is over the smallest of the two dimensions, right? While in this case, the label goes over the largest of the two dimension. So first, it's actually very similar, but because of this kind of duality with the Schmidt decomposition, this is actually, it contains way more information than the pair lambda I, yi. And the reason why this is true is because the density matrix rho alpha beta of the environment can actually, if you know this too, can actually be recovered as square root of Y alpha Y beta, Y alpha scalar Y beta. So it contains much more information than, for example, the reduced density matrix, and you can prove that the following is true: sum over alpha, Y alpha, Y alpha, Y alpha. So this is the density matrix of my system, and as you can see, it has the fact that we chose basically this single label decomposition where these are orthogonal to each other, E alpha, E beta, delta alpha beta. Allows us to build a decomposition of the density matrix that it doesn't have alpha beta terms. This means that the states Y alpha basically do not interfere with each other. And out of this, you can build a unique ensemble, Q of Z, which is the sum over alpha Y alpha delta of Z minus Z of Y alpha, right? So this means that if this is the global quantum state space, and my system, it's in a single point, because the full system, it's in a jointly pure state. So this means that at the joint level, the global geometric quantum state, it is just a Dirac delta. But then what happens when I project down to my subsystem? This is S E, this is S, and now S is the quantum state space of the reduced system. And this is just a cartoon. It's not S can be, but it's actually embedding S. Let me call this the state space of my system S into the joint state space. It's actually highly non-trivial. But if you do, then you realize that this is the situations, basically, right? And each one of these points is the collection of y alpha, which means that basically this gives you a notion of ensemble that with probability y alpha, the pure state of with probability y alpha, the state of my system will be the ket y alpha. And now, obviously, and this is one of the interesting things that that I'm trying to build, is that if your global system evolves unitarily, which means that there is a global Schrödinger's equation, then you can decompose this into its local part, which is H system plus H environment plus their interaction. And you can try and extract an equation of motion for y alpha and z of y alpha from this. I'm not going to go through the details. Z of, let me just call it gamma alpha of t. And so you can study the full unitary evolution for the jointly pure state by looking at the equations of motion for y alpha and gamma alpha of t. And so modeling of the collection of the ensemble gamma alpha, y alpha gamma alpha will give you basically a theory for your globally pure state. So the idea here is that by studying statistically these kinds of ensembles, by thinking at y alpha as a physical property carried by the state gamma alpha, what you have is that you have a situation in which you have points, states on a manifold. They carry with them a certain probability mass. And as a result of the evolution, these points exchange this quality, this probability mass with each other, which means that the local state, so the geometric quantum state of my system is the result of all the possible ways in which my system is interacting with an environment. And you'll see that there are very interesting considerations that one can do. And let me actually open up a file. One second. All right, so this is a numerical simulation of what I just described, right? There is a globally pure state, and in this case, this is a simple qubit, a two-level system with the physical instantiation of a spin. There interacts with, I think these are 10 more qubits, 10 more spin 1/2, with a certain Hamiltonian that is, I believe, the XXZ Hamiltonian. And at t equals 0, the globally pure state, it's in a tensor product state, which means that being in a tensor product state, the local state is also a pure state, which means that my geometric quantum state, the geometric quantum state of a single qubit, it's all concentrated in one point. So this is the Dirac measure we've been talking about. But what happens as I let time flow? As you can see, the probability, as I was trying to explain before, over time, the presence of an environment changes the state of my system. And the way it does so, this is kind of a very intuitive picture, but this is exactly, but I think it's a fair representation of what is happening. So when you look at the structure of the way the system interacts with the environment, there's usually a decomposition as a sum of operators. For example, when we have a two-level system that interacts with an electromagnetic field, you can have two kinds of interaction. If my two-level system is in the excited state, what can happen is that the system gets de-excited and it emits a photon as a result. And this can be written as a product of two operators, one acting on my system and one acting on the field. So basically, you destroy an excitation from the system and you transfer it to the field. And there can be two of them because the reverse process can also happen, right? The system can be in the ground state, can receive a photon and get excited. And so this is written in terms of the product of a raising operator, one that creates a local excitation while destroying a field excitation, lowering the number of photons. So this is usually written as a linear sum of operators, and that sum dictates the way the various ways the system can interact with the environment. Now, if at t equals 0, all the probability it's in one point, and I let time evolve, what happens if these different ways the system can evolve are not compatible with each other? What happens is that the environment is kind of like pulling the state of the system in different directions. And the number of these directions is given by the number of different processes that can occur. But as a result of this pulling things apart, the probability distribution gets split into parts, and a certain amount of parts goes into one direction and another amount goes into another direction. And the way this process continues, obviously, because it's continuous over time. So there is kind of like a fractal structure, which and there are certain time scales that are evident, right? This is the first time scale. 1 point goes into 3. Another time scale is when you can kind of see, this is more clear. One of these clusters went into 3 again. And if I go more, you can see that each of these 3 points splits into 3 points because it's exactly the same kind of mechanism always at play. Is the environment trying to pull the state of the system into non-compatible direction. And as a result of that, the only way the system can basically cope with maintaining an integrated probability equal to 1 is by redistributing probability to its various points. And so the way this happens is, as you can see, highly structured. And this structure is just a reflection of the way the system interacts with the environment. And if you're wondering why the number 3, this is, again, related to the structure of the interaction. And the way this goes is as follows. Let me go back to... So... in a so-called nearest neighbor situation, we have in a 1D geometry, we have a spin 1/2 that interacts with 2 neighbors. This is like a magnetic dipole kind of interaction, and in which my spin, my magnetic moment, interacts with the magnetic moment of the 2 neighbors. And so here we have 3 forces at play. We have my local, I mean, if I am one of these of the spins in this chain, I have three forces that are forcing me to change. They're trying to change my state. One, it's a local force, right? There is a local Hamiltonian, there is a local magnetic field that tries to change my state in a way compatible with the with unitary evolution. But there are also two more forces, right? I also interact not just with the local field, but with the magnetic field of my right neighbor and with the magnetic field of my left neighbor. And as a result of that, my right neighbor, through the interaction, tries to change my state in a certain direction, and my left neighbor in a slightly different direction. And so this is why you see the formation of three new clusters. One is the local force, and two is because I have two nearest neighbors with whom I'm interacting. And again, as you can see, this process continues, right? It just keeps going until you don't see the clusters anymore. And the color of the point that you see, maybe you can see that this is that there is one a bit more brighter and the other ones are more red. The color is the probability mass. Excuse me. The color is the probability mass, which means that it's the value of y alpha. So a brighter color means that that point is carrying more probability mass within. All right, and so this process occurs continuously, and it kind of does in a self-similar way, because again, these forces that pulls the state in different directions, they're just there at each time. And though we can clearly see this formation of the cluster only if we go through finite time steps, this process is always occurring. But of course, after a certain time scale, we're not going to be able to distinguish the clusters anymore, because they're going to cover the whole state space. So as you can imagine, there can be interesting connections and interplays with the notions of with dynamical systems notion, like the notions of attractor, ideas from ergodicity, and so on and so forth. All right, I think it's time. It's 1 minute to 8, and as always, I'm here to take questions.
Thank you very much, Fabio, for again a great lecture. And my apologies because I missed the beginning.
No worries whatsoever.
I was stuck in some other meeting that was way more boring than this. Sorry for that. I see there is a raised hand by Jean. Jean, please. Ilya, I think, already gave you the right to speak. Just unmute yourself and ask your question.
Thank you. So I'm just trying to understand what's going to happen on the sphere if we start in a state that's not a pure state. And so we don't have, our probability mass function doesn't start as a point, but as some spread out.
This is not a pure state, right? So it's just going to continue.
Yes, but so if we start out with our probability mass being at a point, then that's kind of why we have these splitting into more points, if I'm understanding the system correctly.
So it's clearly evident when you start with a single point, because there's nothing else, right? So it's easier to see. But as I was saying, this process is constantly at play, right? It's not like over time, I've changed the interaction. Once I fix the structure of the interaction, that's the way they are, and they'll just keep doing what they do, which is this pulling the state of the system apart in different directions.
Okay, and so if we let it go for long enough, we get something that's approximately uniform, I imagine.
So I would imagine so. But I also know physically that this is not always true, right? There are systems with conserved quantity. So, okay, this is actually a very interesting question, of which I do not know the general answer, but there are several comments here. So first is that this question you're asking is about thermalization, right? So this is the global system in the language of dynamical systems. It's an integrable system. That's because this is a linear space of dimension d that contains d conserved quantities. So this is an integrable system, but some of these quantities may be associated with stuff that are highly non-local. So when you look at local evolution, they look ergodic, but actually extracting the conditions when these happens and kind of predicting, given a Hamiltonian, if this is going to happen or not, it's a fully open problem. We have instances, well-known instances, where this is true in very specific cases, and when this is false in other cases. So an example is the so-called XAZ model, which is an integrable model, but that locally behaves as a fully ergodic, I should say, for one-body observables, behaves as a thermalizing model. And this is one example. The other example is the so-called many-body localized systems. So these are systems in which, if we look at the chain, this is not clean, but locally your magnetic field fluctuates, and maybe also the interaction fluctuate. And when there is too much disorder, basically the system gets stuck in one of these states and it cannot escape. And so there you lose this picture of ergodicity. Intuitively, you should also lose the fact that this probability distribution spreads all around the sphere, but it should be able to populate only certain regions. But again, this is building out of intuition from other areas. So the actual situation here in the geometric picture, I'm not sure what is it, but I do think that this is a good tool to investigate these questions, and this is actually what it's one of the things I'm doing. I'm trying to come up with a comprehensive theory where I can say, in these situations you're going to have a good decision, and in this other situation you're not. But this is actually a very hard problem. So yeah, does that? Okay.
Thank you. There's a question by Camille. Camille, please go ahead.
Yes, no, I have actually a kind of comment and question also related to that, kind of follow-up. So yeah, again, I guess, so this periodicity or thermalization behavior would also depend probably of the initial state, and maybe also obviously of the number of spins. So for instance, if you consider only, so your spin of interest interacting with only one other spin,
right,
and if you start, I don't know, in the excited state, you would expect kind of periodic behavior.
You do.
Yeah. But maybe if you increase the number of spins, maybe that's not so obvious, and depending also on the steady state, on the initial state, I guess the situation might change quite a lot.
Yes, no, you're absolutely right. So first of all, yes, you can do the same analysis in which you have one spin that interacts with one other spin, and this is just 2 points orthogonal to each other, just moving on the sphere. Now, so you do have periodicity, right? However, you can also play different games, right? You can play a game in which the interaction between these two spins, it's actually time dependent because it's a driven system, right? And then you can have other kinds of behavior in which the geometric quantum state doesn't evolve periodically, but maybe it actually settles on a certain behavior that it's fixed in time. That being said, yes, the idea would be that in the limit for the environment that becomes significantly larger than the system, and for physically reasonable states, so not for all possible initial states, but for classes of initial states that we know to be of physical relevance, there is a rough characterization of those in terms of the width of the energy width of the probability distribution, but that for those you should recover thermization. Yes, that's exactly right. So it's in a certain regime, but it's also the problem of thermization. I think it's even more complicated than that, because I think thermization, it's one of those, it takes three to tango situation in which the notion of thermization does depend on the initial state. It will depend on the observable you're going to look at, and it obviously will depend on the Hamiltonian. So if one wants to be comprehensive, one should study, given a certain Hamiltonian and certain classes of initial states and certain classes of observables, when do we have thermization? Now, in this case, the class of observable is implicitly defined as the class of one body observables, because we're looking at the geometric quantum state of one ensemble. But yeah, you're absolutely right, Camille. And the intuitive picture would be that, so if you count the number of points here, this is equal to the dimension of the environment. So as the environment grows and grows, this number of points will become kind of indistinguishable from a classical field, a classical probabilities, a continuous probability distribution on the sphere, right? So then the question is this probability distribution highly skewed around one single point, or does it actually have all the probability mass spread around it, or maybe it's layered so that it can be described by a Gibbs ensemble? So the question is, in that limit, is this classical probability field something that has to do with thermal equilibrium or not?
Thank you. Thank you, Fabio. I don't see any other raised hands, and I think I don't see any questions in the Q&A, but please, Ilya, correct me if I'm wrong. So Fabio, then it is my pleasure to thank you again very much for another fascinating lecture. I will watch the video of the first 15
No worries.
No, otherwise I missed the highlights of your lecture series. Yeah, and maybe again an invitation to the participants to join us again next week, because next week would be the grand finale of the of the lecture series, and I'm sure Fabio has some fireworks prepared for us for next week. So thank you very much, everyone. Thank you very much, Fabio, for your time and for preparing such nice and interesting lecture. Thank you, Ilya, for starting the webinar this morning, and Camille for introducing us to Fabio. So thank you very much, everyone. Have a good evening, and please keep staying safe. There is less COVID almost everywhere, but it's still out there. Yeah, so take care. All the best. Thank you very much. See you next week. We can have a chat next week before your last lecture. Thank you.
All right.
Thank you very much. Bye. Bye-bye.